Good evening, good evening, everyone. Welcome to the Amateur Radio General Class session number 5. During our previous session, we looked at the following topics. We had a review of logarithms. We then went on to discuss decibels or dB associated with power and did some worked examples. We also discussed circuits of resistors in series as well as parallel, and we also did some worked examples. Then we discussed inductors, similarly in series and parallel, with worked examples. And then we ended the technical session with a discussion on capacitors in series and parallel, also with worked examples. So agenda for this evening. So we will just go over again the material that's available for the technician class course. We'll have a look at where we are in the curriculum. We'll mention again the practice exams that are available. Also, we'll go back again into the Zello application that's available for persons who would like to interact with React. We'll present the links to the material for this course, the general class course. And I don't think we have any Q&As from last time, so we'll go straight into the technical topics. We'll start off with mutual inductance. Then we move to transformers, and then we'll do some calculations associated with transformers and worked example. Then we will discuss the wire sizes associated with the windings of transformers. Then we will discuss impedance ratio, that would be ratio, as well as the works example. And then we will discuss wire wound resistors, the properties of them. And then we go into the different types of capacitors, the characteristics of ceramic and electrolytic capacitors. Then we speak about toroidal ferrite core inductors. We'll discuss what ferrite material is about. And then we will end the technical session with self-resonance. Then move on to our usual question pool review that covers all of the theory that we would have done this evening and the associated questions. All right. So just a reminder for persons that there are 3 levels of exams, 3 courses associated with the FCC syllabus as far as amateur radio qualification goes. There's the technician or level 1, there's general level 2, which we are presently doing in the course. And then of course, subsequently we'll do the extra class. But for persons who are new to the general class, we do have an on-demand technician class available to you. And the link on your screen, you can get all of the documents associated with the technician, all the slides, as well as the text and also the recording. So just a reminder, please, if you have not yet taken the technician class course, this should be your focus. No need to discontinue the general class, as we do try to pull back some of the information from the technician for you, but the focus should be on the technician if you have not yet studied or covered that material. So by now, we're in session number 5. Several weeks have passed, and there are really 16 sessions in the technician class. So we're hoping that most participants are well on their way to covering the material in the technician class course, because it builds as we see or shall see. Right. So coming to our general class syllabus and the curriculum, where are we? Well, we will be completing the electrical principles. We just have a couple of items of theory, and then we'll move straight on to the circuit components. So this is where we are in the course. Reminder always to consider taking the practice exams. These are the links. Again, we keep getting a lot of interest in persons asking about the Zello channel. So we just have it up as a slide. We'll do so for the next little while or so to remind persons that's the channel React members, where you can interact with React and also get to practice radio type operations using an app called Zello. So the material for this course, the general class level 2 that we are presently doing, The first link on your screen is to all of the slides and handouts that we would have provided to participants, such as the Part 97, the actual question pool, and another text that may be a good reference as well as you study. And then we have all of the recordings. Once they stick, we do in fact produce this playlist that's updated every week or so. So if you missed any of the session, because Friday evening is not the most convenient time to everyone, we do have the recordings, or we try to make the recordings available so that no one will miss out. And also it serves as refresher if you want to look over material that we covered. You can play back at your own pace. You can even look at it on a smart TV, for example, using the YouTube app. All right. So just a reminder, these are all of the texts that are recommended. If you so choose, it's not necessary that you procure any of them at all. They're available on Amazon or the author's website. Highly recommended. So these are the texts that we do recommend to students if you wish to avail yourselves of any text. It's not required, but highly recommended. So we had no outstanding technical questions from last session. So let's go straight into the material. So we put the slide up just as a reminder that while we are talking electronics, electronic theory and electric circuits, and we have wiring diagrams or schematics that discuss the various components, electronic components such as resistors, batteries, capacitors, inductors, and so on, we do use from time to time the water analogy, right? So whereas the battery is like a pump in a water circuit where water circulates, in an electric circuit, electrons are what circulate in an electric circuit. So we just always like to keep that on the back of our mind when we're talking about schematic diagrams and electric circuits. We're already familiar with many of the concepts because it operates very close to the way water operates. You know, there's a current, you know, we go to the beach, there's a current flowing. So you'll hear us talking about current in an electric circuit. Well, it's quite similar in a water circuit. So you probably know a lot more than you thought you did. Right, so just to apply the knowledge. All right, so let's reintroduce the idea of what an inductor is, because we're coming to transformers shortly, and transformers contain coils or inductors. So just remind ourselves what an inductor is. Essentially, it's a coil of wire. All right, so when you see inductor or inductance, just think of a coil of wire and energy being stored in magnetic fields. And of course, we have the symbol for an inductor. And anytime you see the symbol, you'll sometimes see them with other symbols similarly and forming other type of components. So the one we'll come to shortly are transformers. And you will see that transformers use the inductor symbol. Why? Because transformers are consisting of coils of wire around a core. Right. So we had discussed inductors and the fact that they have inductance. What we need to be aware of is that when a coil of wire is energized and there's a alternating current that passes through that coil of wire, what happens is if you have another coil of wire nearby or wrapped around it or in a, let's say, a core, what happens is that even though the current is passing through that one coil of wire, it induces a current in the other coil of wire through something called mutual inductance. So that's why we say here that mutual inductance occurs when a current flowing through one inductor induces a current in a nearby inductor. So it's because of the flow of that AC current that's going back and forth, the magnetic lines of flux are cutting the other pieces of the other wires or the other coil and inducing currents inside of there. And that's how transformers are created. You may be familiar with transformers on electricity pole. You'll see them. Sometimes you have an adapter, or what we call a power pack, that you plug into the wall to break down from your 120 volts AC to maybe DC. The older ones used to have the transformers. The newer ones, well, they are switching circuits or switching mode power supplies, but the older ones, the heavier ones, the bigger, larger ones, and sometimes they would hum a little bit, you know, that contain transformers. And transformers are essentially what you're seeing on your screen here. It's a coil of wire and another coil of wire wrapped around an iron core. So remember we said mutual inductance. So when current flows through one coil of wire, that magnetic field is set up. It's going back and forth, and it induces a current in the other coil of wire. And we'll come to see that we can actually calculate in a transformer, just how that property goes, the current and the voltage and so on associated with that transformer operation. And we'll see how we can move or change the voltage from one voltage value to another using that property of mutual inductance and employing transformers. So you probably are already familiar or seen what a transformer is, but we'll get into a little bit of the mechanics of how it works, as well as to do some calculations. And on the right-hand side here, we'll see that this is a symbol for transformer or a transformer. And you'll notice, as we had mentioned before, this is an inductor symbol on the left-hand side, and this is an inductor symbol on the right-hand side. And then we have iron core that's represented by these two parallel lines. So together, these two inductors put together with the iron core form a transformer. So you'll see how we use or reuse the inductor symbol in creating the symbol for a transformer, because that's exactly what it is. Two coils of wires or inductors that are employed together. And as we said, the magnetic lines of flux that are created, and when you supply voltage to one side, alternating current voltage, it cuts the other coil and causes a flow of electrons on the other side. So that's how a transformer works. So that's the next point. The concept of mutual inductance is used in transformers. So when this inductor or this coil of wire magnetic fields are created, it induces current flow in the other coil of wire, and that is mutual inductance. And we need to know the definition of mutual inductance for the exam, because this is an exam question. The tip, as we have been giving all students, anytime or most times you see writing in this yellow color, that is usually verbatim an exam question. So you should be paying particular attention to the stuff that we have in yellow on your slides. Everything is important to understand, but in terms of preparing for the exam, remember we are light touch theory and exam focused. So we're putting it out there, what you can expect to get in the exam. And remember, in this course, we cover every single question that you can get in the exam. It's question pool based, and we do all the theory for every single question, and then we look at every single question. So in the exam, there should be no surprises. In the general class, we have about 430 of them, so it's quite a bit, but we try to go through and make sure that every participant, we all are familiar with every single one. All right, so this is a definition you need to know about mutual inductance. So we just discussed what it is. The definition goes as follows. Mutual inductance causes a voltage to appear across the secondary winding of a transformer when an AC voltage source is connected across its primary winding. So let's break that down. So it's what we just said, mutual inductance. What does it do? It causes a voltage to appear across the secondary winding. So let's look at that. So we have a primary winding. This coil of wire here is the primary winding, and we apply a voltage, an alternating current voltage. And then we say that that mutual inductance will cause a voltage to appear across the secondary winding. Well, this is the secondary winding here. So the voltage that we apply, we plug this into our wall outlet, right, into a receptacle outlet, and it has alternating current that flows here, but it sets up through mutual inductance a flow of current in the secondary winding or the secondary coil. That's what this first part of the definition means of a transformer. So this is a transformer. You have the core or the iron core, and you have the two coils of wire around it. When an AC voltage source is connected across its primary, all we are saying is that we apply an alternating current voltage source to the primary. In other words, we plug it into the wall, this side, but a current flows on this side due to mutual inductance. So this is a definition. It's an exam question. All right, so let's talk a little bit about transformers, right? So we just introduced it. So again, on the right-hand side, we have a similar set of diagrams. We have a primary coil across an iron core, and then we have a secondary coil also connected, or also wrapped around the iron core, right? And these wires are insulated. So even though it's a coil of wire on an iron core, they don't actually conduct, right? So it's insulated, right? So just bear that in mind. But this is how it's set up. And we have the primary coil, and the primary coil is usually where we apply the voltage coming in, and the secondary coil or the secondary winding is where we expect to get a voltage out. And sometimes what we do is we apply a voltage of a particular value, and depending on the ratio of the turns of the wire, so we have a number of turns here, maybe 10 turns, and on this side maybe we have 20 turns. the ratio of the voltage is proportional, directly proportional to the ratio of the coil windings. So if we have 10 windings here, it's coiled up 10 times, on the side 20 times. Whatever we put in, we can expect to get a voltage of twice the amount. So that is how transformers work, and it works for alternating current. You must have that current going back and forth so that the magnetic lines of flux cutting in both directions will cause AC to flow on the other side, right? So bear in mind, we're talking alternating current here. So we apply it here. So for example, we apply our usual 110 or 120 volts AC that we get from our house supply, receptacle outlets in a home. And on the other end, because it's a 1 to 2 transformer, a step-up transformer, because we are stepping up the voltage, or we want to step up the voltage. So we apply a transformer that has this property, double the amount of coils on this side as on the primary. So we get twice the voltage. So whatever we put in here, we get twice out. So that's step up. And we have the other way as well. If we have the primary that has more windings and the secondary has less windings, that's a step down transformer, because whatever we put in, we'll get less on the right hand side. So we have 20 windings on this side and 10 on the other side, then it's half. So if we put 220 in, we will get 110 out. So that's the concept of how the transformer works with alternating current voltage. So we have a couple points here that you can read on your own. Just to note that a step-up transformer can become a step-down transformer by simply applying the voltage in the opposite direction. Instead of putting it to the primary coil, we put it onto the secondary coil. And we will see some calculations associated with that shortly. And we will also see that, there are some prerequisites as well. If we're going to use a step-down transformer as a step-up and vice versa, we should be very careful. We'll see and come to those points very shortly. All right, so we come to some transformer calculations. So on your screen, we have what a transformer looks like. We did say we have a primary input or coil. So VP represents the primary voltage in. And on the right-hand side, remember it's a transformer, so it's going to transform the voltage on this side to this side, but it's alternating current. So we'll get another voltage called the secondary voltage. So this is the in and this is the out. But remember, we can swap, right? Or we should be able to swap under certain conditions. And we're just introducing a formula here. It's not necessarily that you learn this per se, but we need to be aware that the property that we talked about, remember we said that there's a ratio of the number of turns of the coil on one side versus the other. There's a ratio. So maybe we have 10 turns on this side and 20 turns on the other side. Well, that's a ratio of 1 to 2. So the ratio of the turns of the coil, 1 to 2, is also the same ratio as the voltage. And that's what this formula is saying here. The primary voltage over the secondary voltage is equal to the number of turns on the primary side over the number of turns on the secondary side. So it's a ratio. It's the same ratio of the voltage to the number of turns. And that's the beauty about transformers. You can design a transformer for whatever voltage in to get a particular voltage out by simply having the ratio of the turns, the winding, to match what you want to get out. So that's the transformer formula. And we have broken it out a bit for us to understand. Again, this fancy formula here, all it means is that the primary voltage divided by the secondary voltage is equal to the primary number of turns over the secondary number of turns. And we need to know this for a purpose to derive this other formula, which we'll be using in our calculation itself. So we'll see here that the secondary voltage is equal to the primary voltage multiplied by the secondary number of turns over the primary number of turns. How did we get that? What we did is we used this transformer formula and we did algebraic manipulation to solve for the secondary voltage. Why do we do that? Because we want to know if we want to achieve a particular secondary voltage, what must be the primary voltage input and what must be what we call the turns ratio. That's the number of turns in the coil on the secondary side divided by the number of turns in the coil on the primary side. So we have just used this formula that is the transformer calculation formula, and we have done some algebraic manipulation to solve for what is secondary voltage equal to. Right? So this is what we'll be using for our calculations. And this secondary turns over primary turns is what we call our turns ratio. So you will see that term coming up a little bit. All right, so we have a worked example for a question that you'll get in the exam. So we're talking transformers. On the right-hand side here, we have set up a diagram showing the nature of the question, right? So we'll come to the diagram in a little bit. So let's deal with the question. It goes as follows. What is the voltage output of a transformer with a 500 turn primary and a 1500 turn secondary when 120 volts AC is applied to the primary? Okay, a pretty long question here, but let's dissect it. Let's break it out and let's see what it's telling us and what it's asking us. It's asking us, what is the voltage output? And I've just put in here secondary. So we want to get the secondary voltage output. And that's why earlier we solved the equation for secondary voltage equal to something, because that's typically what we need to solve when we get these types of questions, right? So they have asked us for the secondary voltage or the output voltage, right? That's what we're trying to solve. So therefore, whatever the answer will be in volts. Okay, so of a transformer. So we know it's alternating current. Once you talk transformer, it's an alternating current that we're dealing with. And they have given us the number of turns in the primary and secondary. They have said that the primary is 500 turns. So if we were to look at this little diagram here, we will see that this is the primary input side of the transformer, this coil, and there are 500 turns, right? And they have told us that on the secondary side, we have 1,500 turns, 1,500 turns on the secondary. So this is our secondary coil on this end, and there are 1,500 turns on this side, right? 500 turns in the primary, 1,500 turns in the secondary. And then we want to know what is the voltage output. Of course, it's going to be AC, so that we have VAC, voltage AC. On this side, what is it going to be? If it is that we have an input that's applied to the primary of 120 volts AC. And this is a kind of what you can see in the house, most Trinidad and Tobago for sure, the United States and a couple of countries, it's 120 volts typically that you get in the receptacle outlet in your home, right? Other countries, you have 220, 240 or some other, another voltage. However, we are dealing with this question here. So we have just broken out this question into a diagram, and hopefully we can see the question on the screen here. 120 volts input line current into this coil of the transformer. It's 500 turns. And what is the voltage output on the other side? Because this coil is 1,500 turns, and we should probably recognize that this is 3 times as much turns as the primary. The secondary has 3 times as the primary number of turns. And persons who are clicking already should probably say, well, wait a minute, whatever the voltage input is in here, the output is going to be 3 times the input. And you'll be quite correct, and we'll see how we come up with that, right? So some of you probably have already realized that based on the theory that we just covered. But let's work it out. Let's use our trusty formula and let's get the result. So again, we use the formula that says the secondary voltage is equal to the primary voltage multiplied by the turns ratio. And what is the turns ratio? The turns ratio is the number of turns in the secondary over the number of turns in the primary. All right, so let's solve, or let's insert, or let's substitute those values and solve for what the secondary voltage or the output voltage is. Secondary voltage is equal to, what is the primary voltage? They gave us in the question, it's 120 volts AC. So we substitute primary voltage with 120. Then we multiply it by the turns ratio. To get the turns ratio, we need the secondary number of turns over the primary number of turns. They gave us that, did they not? Yes, 1,500 turns secondary. So we put that on the numerator on top. We replace secondary turns with 1,500. Then we need to get the primary turns at the bottom or the denominator. Did they give us that? Yes, they said 500 turn primary. So we substitute primary turns 500. And that's what we do. We come to the next line in the equation. Secondary voltage is equal to 120 multiplied by, well, 1,500 divided by 500 is 3. So we're seeing already that, yes, we kind of figured out, well, it's going to be 3 times the voltage, right? So we're quite correct. But this is the formula here, and we're applying it. And we're seeing here that 120 multiplied by 3 is 360. 360 what? Volts. And it's volts AC. That's the secondary voltage. 360 volts AC, that's the output that we're getting from this transformer on the basis of us putting in 120, on the basis of 500 turns in the primary, 1,500 turns in the secondary, which is a 3-to-1 ratio. All right, so that's what we need to be aware of here. That's how the transformer works. So this is the question, and this is the answer for the exam question. All right, let's do a couple more slides before we take our break. All right, So again, we have this setup here as transformer again. Notice that this particular transformer, we are saying here, this is the primary side and this is the secondary side. So if we have it set up like this, primary, and you have a larger number of coils on the primary, and on the secondary side, you have a lesser or lower number of coils, you probably would recognize that this is a step-down transformer. Whatever the input on this primary side is going to be less, or in a ratio less than the primary, right? So if it's 200 volts on this side, maybe it's 100 volts on this side, depending on the ratio of the turn. So this is a step-down transformer, but we are saying that this is a 4-to-1 step-down transformer. So essentially, whatever on the left-hand side we put in here, we'll get quarter out on the right-hand side. That is essentially what it means to be a 4-to-1 step-down transformer. All right. Now, remember early on, we said that a transformer, normally you will put the input on the primary and get the output on the secondary. But you can reverse it. You could actually put the voltage input on the secondary and get a voltage output on the primary. How is that possible? Well, the same inductance, mutual inductance that will occur had you put the alternating current voltage on the primary, it induces a current in the secondary. If you reverse that and put the input signal of that voltage or that alternating current voltage on the secondary, it will dutifully present mutual inductance to the primary coil, and it will output a voltage on the primary. I mean, it's a step-down transformer, yes, except that instead of us putting the input signal here, we put it on the other side. Nothing says we cannot. Of course, there are some cautions that you'll see in a little bit that we need to take if we're doing something like that. But it just shows that essentially you can put a voltage on either side and you'll get a voltage out on the other side in proportion to the coil. So this is what we have done here. This is normally the primary, which we would normally put the input in. And this is the secondary where we normally take the output. But we're reversing it. We are putting the input into the secondary. And we are going to measure and see what voltage we get on the other side, the output side, which happens to be primary. So hopefully that doesn't confuse us. We are just reversing the role of the step-down transformer and turning it into a step-up transformer. All right, so you probably already guessed, well, wait a minute, if it's quarter going one way, if it's going the other way, it's going to be 4 times, and you'll be quite right. If we were to put a voltage in here, and the output will be quarter, if we were to put the voltage on this side, on the other side here, we'll get 4 times, right? So it works in both directions, right? So that's actually an exam question, and here it goes. The output voltage, if an input signal is applied to the secondary winding of a 4-to-1 voltage step-down transformer, instead of the primary winding, is the input voltage is multiplied by 4. All right. So that's what this means, what we just said here. It sounds a little bit, around the road. It's a little bit, could be a little bit confusing, it seems, but we have just explained what it means here. This is a step-down transformer, right? So we're saying that it's applied to the secondary winding of a 4-to-1 voltage step-down transformer, but we're applying it to the secondary of the step-down transformer. So we're actually making it a step-up transformer. Normally we'll apply the voltage here and get an output here of a quarter. But because we're applying it to the secondary, then on the other side, because it's a 4-to-1, we multiply by 4. And if we were to use this trusty formula, it will work out like that. So we just need to know this for the exam. If you put the input on the output, you'll have an output on the input of 4 times. And that's what this cryptic statement says here. So hopefully we have understood that concept. So let's do a couple more slides before the break. All right, so we did say that there are some cautions if it is that we are going to use a transformer that will normally be either step down or step up, right? In the reverse order. So we're using a step down transformer as a step up. We say here, be careful when reversing a transformer from step down to step up. The current in the primary winding is higher than the current in the secondary winding of a step-up transformer. And that's one of the things we need to bear in mind, right? And the reason for that is V is equal to IR. And of course, you have the conservation of energy. Yes, there are some losses associated with the magnetism and then the core and all of that. But essentially, if you have a voltage on one side, a current flows. And if you have the voltage on the other side of the transformer, let's say a higher voltage, then you will have a lower current. But if the voltage is lower, then the current will be higher. So they're just telling us that in the primary winding, the current is higher because of the current in the secondary or secondary step-up transformer, right? If it's a step-up. And of course, the conductor of the primary winding is larger. Why is that? Because we need a larger current than the diameter of the secondary winding in a step-up transformer, right? So step-up transformer here, for the primary, the winding is going to be thicker. The wire is going to be thicker compared to the secondary. It's going to be thinner. Because why? Because a larger current will flow here. And because it's a larger current, we need a thicker wire for the current to flow. The voltage will be low on the side, but the voltage will be higher on the side, but the current will be less. Again, V is equal to IR, right? Okay, and then if you use a step-down transformer as a step-up transformer by connecting the input voltage to the secondary winding, which is what we just did in the previous question that we tackled, the wire on the winding may not be able to handle the higher current and burnout. So if, for example, we apply the voltage here, and it's going to reduce the voltage on the primary side, well, as an output, what is going to happen? Because the voltage is reduced, the current is going to be higher. And that's what they're telling us here. Just be careful that this winding, which is normally an input, which will be used as an output if we reverse the role, make sure that the winding here is thick enough to handle the current that is going to be the output. So let's just be careful about that, right? So that's just information. As an amateur radio operator, you may be designing circuits and you may be using used parts or new parts and building circuitry and so on. You may be repurposing transformers, and you need to know the property of those transformers to be very careful. So that you don't, burn up a transformer. A pretty good transformer might be expensive, but because you weren't aware of this safety measure, you're going, burn the coil and you have to replace it. And sometimes these things can catch a fire and all of that. So again, safety first. We need to be aware of this as we build circuits, repair circuits, replace devices. We need to know these things. All right. So let's deal with just one more slide before we take our break. All right. So we just discussed the fact that the primary side of a step-up transformer. So this is a step-up transformer. How do we know that? Because we have on the input side or the primary side a lower number of coils. On the output side or the secondary side, we have a larger number of coils. So that's going to be a step up, because we are aware that when you apply a voltage here, depending on the ratio of the number of turns of the coils on the primary versus the secondary, if it's higher on this end, we know it's going to increase the voltage. And that is called a step-up transformer, right? So if we have this kind of situation here, primary and a secondary step-up transformer, the winding on the primary side is normally larger. The thickness of the wire on the primary side is going to be thicker. It's going to be larger diameter compared to the secondary. Why? Because the voltage being low on this end will mean that the current will be higher. On the opposite end, the voltage is going to be higher, which reduces the current flow. Again, because V is equal to IR, right? That's a relationship. And the higher the voltage, the lower the current. The lower the voltage, the higher the current, because it's the same amount of energy that is being circulated on this side as on this side, or just about, some little losses and so on. But we need to be aware of that. And that's the bullet point here, and it's an exam question. The primary winding of a voltage step-up transformer is usually a larger size than that of the secondary winding to accommodate the higher current in the primary. Let's dissect this. The primary winding of a voltage step-up transformer, that's this side, primary winding, it's a step-up transformer. It's usually larger, so we're saying that this is thicker diameter than this coil, than that of the secondary winding. This is the secondary winding. So this is thicker than this. And why is it so? It is to accommodate the higher current of the primary. You're going to get a higher current on the primary versus the secondary. Why? Because the voltage on this side is going to be lower, so therefore you have a higher current. When you step up the voltage on this side, the current is going to be lower, again, because of the relationship between voltage and current. Again, Ohm's law, V is equal to IR. You can use that as an equation to understand this, right? All right. Okay. So let's just take a break, 2-minute break. Get up, take a little stretch, maybe have some water, a bathroom break, and we'll be back in 2 minutes time. Okay, good evening, Iskin. So you can use the Q&A option in Zoom. Good evening, Adish. Great to have you. Ramzan, excellent point indeed. So Ramzan is advising that when you're testing transformers, make sure you use fuses in line with the correct values. Right? So excellent suggestion indeed. All right. So let's continue. So this is where we left off, talking about the various sizes of the conductors or the coils and associated with the current. All right. All right, so we're now coming to another related topic of impedance ratio. So we're saying that apart from transforming voltages, which is what we just showed that a transformer does, we have one voltage AC coming into the transformer and we're transforming it to another voltage AC, right? Alternating current voltage, one value to the next. And by the way, you can have a one-to-one transformer as well, the same voltage in, same voltage out to have as an isolation transformer. So it doesn't necessarily have to only be step up and step down. You can have a one-to-one. You can even have variable transformers as well, or what you call variacs, right? So let's look at another function of transformers, which is to transform impedances, except that the formula is based on the square of the turns ratio as opposed to just the turns ratio. Remember, in the voltage case of transforming voltages, we just use the turns ratio, which is the secondary number of turns over the primary number of turns. But in the case of impedances, which we can also transform impedances, we need to use the square of the turns ratio, right? So that's just the point here. Again, not particularly important for the exam, other than to explain how we get the formula that we're going to use for the calculations, right? So the formula is turns ratio, which is what we're going to be asked to solve. What is the turns ratio? Is the square root of the output impedance over the input impedance. So in the same way that we can use a transformer to transform a voltage to another voltage, we can also do impedance matching by using a transformer. And how do we calculate the turns ratio? We use the square root of the output impedance over the input impedance. So let's do a question which will hopefully make that a little clearer. So this is a worked example. It's an actual question that you will get in your exam. What transformer turns ratio matches an antenna's 600 ohm feed point impedance to a 50 ohm coaxial cable? So let's dissect this question. Let's break it up. And this is a very practical question because sometimes this is what hams are required to do. Sometimes we have to construct impedance matching transformers or balance or different things that we have, and we have to work out what the turns ratio is. You have one coil and then we'll have another coil, and what is the ratio of those two, right? So existing hams in the class or persons who might have tried to construct matching networks and so on before, this is important to you, and you're getting the formula that you have to use. You don't always have to use a lookup table. You can work it out yourself. And this is actually a very practical example. So what we have done here is show exactly what they've asked in the question. They want to know the transformer turn ratio. So this is a transformer, we're building it over a toroidal core, and we'll come to toroids in a little bit. So you have one coil of wire wrapped around this disc, and then we have another coil of wire also wrapped around, and that's a transformer as well. Two coils of wire wrapped around a core, all right? It's just a circular core. And we want to know how many turns would the secondary need to be with respect to the primary. We can work that out because what we're trying to do is match impedances. And this is a practical example. You have a radio here, a transceiver, and you're connecting it to this antenna. But the radio itself is expecting a 50 ohm. It's expecting to see 50 ohms load. But this antenna itself, because of how it's constructed, the feed point of the antenna is not 50 ohms at all. It's 600 ohms. So we have just sort of diagrammed out this question that they have hypothetically put to us, and see that this is a very practical, we have a 600 ohm antenna, ladder line coming from it, and the impedance there maybe is 600 ohms, it could be 500 ohms, it could be 470, it could be something like that. And we have to connect that to our radio. Can we connect it directly? Well, We remember we say Ham's a matchmaker. So we want to match this 50 ohms to this 600 ohms, and we can use a matching transformer like this. But we need to know to calculate the turns ratio. And what do we use? We use our trusty turns ratio formula, which we said is the square root all of the output impedance versus the input impedance, right? So did they give us that? Yes, the input impedance is 50 ohms, right? So we have the 50 ohm feed line coming from the radio here. So that's 50 ohms. And then we have the output impedance, which is the antenna. It's 600 ohms at the antenna. And we want to match these two. Yes, we can. So we use our trusty formula. Turns ratio is equal to the square root all of output impedance over input impedance. So we substitute output impedance 600 ohms, and here we go in the next equation. Turns ratio is equal to the square root of 600, which is the output impedance on the numerator, and in the denominator below the line we have the input impedance of 50 ohms. So we put 50 ohms in the denominator. When we divide 50 by 600, when we divide 600 by 50, we come to the next equation. We get turns ratio is equal to the square root of 12, because 600 divided by 50 is 12. And then the next equation, we simply use our calculator and find the square root of 12, which is approximately 3.5. And therefore, the turns ratio is 3.5 to 1. And that's the answer for this question. So we have just solved, if we want to do a matching transformer to match a 50 ohm feed line to 600 ohm antenna, all we do is do a turns ratio of 3.5. So we have the primary, and then 3.5 is the ratio of the two coils together. So you can see this theory has a very practical application. Right, so again, exam question. All right, so let's go on to now some components again, and to discuss some of the properties of these components. So as hams, we need to be familiar with these electronic components. And one of them that we had introduced certainly in the technician class, we talked a bit about it again in the general class when it came to parallel and series circuits, is the resistor. And remember what the resistor does. It resists, right? It resists the flow of current, both direct current and alternating current. It will resist the flow, just like in a water circuit where you have a constriction, and it will cause a resistance to occur to impede the flow of current. Same thing in an electric circuit. So this is what a resistor component physically might look like. And this is the resistor symbol, or one of the symbols that we use for resistors. On the right hand side here, we have quite a few different types of resistors for your information. But let's get to what we need to discuss for the general class in relation to resistors, a very practical consideration. So in the previous slide, we saw that there are different types of resistors. We have carbon composition resistor, so the internals of it is carbon. But then we have a type of resistor that's a wire wound or wire wound resistor, some people call it. So it's really a coil of wire. Now, the fact that we said it's a coil of wire, those of us who've been paying attention may say, well, wait a minute, a coil of wire, is that not an inductor? Aha. So you're starting to see some of the reasons we do this theory, right? So it's RF circuits, it's radio frequency. So it's not only going to be a resistor, this wire wound resistor, but because it's a coil of wire, guess what? It's going to have inductance at alternating current or radio frequency. So we need to be aware of that. There are different types of resistors. As we see, we have carbon composition, we have carbon film, we have, different compositions of resistors. Resistors are made in different, using different material, different construction techniques. But we are talking about wire wound resistors. And we have a cutaway here of what a wire wound resistor looks like, right? So you have the lead here, and then we have a coil of wire, and then you have the output lead. So because this type of resistor is a wire wound resistor, while it's a very high precision resistor because of how it's constructed, we need to be aware that this may not be such a good idea to use wire wound resistors in radio frequency circuits. Why? Because we just said it's a coil of wire, and therefore it may create an inductance. So it has the property of inductance. And as we did in the technician class, also a bit in the general class so far, you'll notice that we have, if we want to create LC circuits, right, where we'll have reactance, we put capacitors, we put inductors. and that modifies the circuit, right? So we don't necessarily, if we just want to introduce a resistance, we may not want to use a wire wound resistor in our radio frequency circuit because we'll be introducing inductance. Why? Because wire wound resistors consist of a coil of wire, which is essentially an inductor. And we have an exam question that's associated with that bit of theory. And here it is on your slide in yellow. Wire wound resistors should not be used in RF, which is radio frequency circuits or alternating current circuits, because the resistor's inductance could make circuit performance unpredictable. So in other words, you have that stray or you have that extra inductance that you weren't designing or catering for. So this is a bit of a warning, and it's an exam question that you need to be aware of. All right, so we dealt with inductors. Let's come to capacitors. So we're just reminding ourselves what a capacitor is, right? It stores energy in an electric field. That's what it does. And we have different types of capacitors. We have the ceramic type, we have the electrolytic type, different construction. And of course, we have the different symbols. So of course, we covered all of this in detail during the technician class, but we're just reminding ourselves what a capacitor is because we're going to deal with some properties of capacitors. We have another slide up that shows the construction of a capacitor. So you have two conductive plates sandwiching a dielectric or an insulating material, right? So that's how it's constructed. So just refreshers, right? So let's come to a bit of the theoretical information about the differences between the two types of capacitors that we dealt with, the ceramic capacitor and the electrolytic capacitor. So ceramic capacitors, they are low cost, relatively low cost, right? And they're often used in electronic circuits. You'll see them if you open up a circuit board, especially those that have discrete components, you'll see them ad nauseum. And the thing about it is that they tend to be relatively low capacitance, right? You hardly find a very high capacitance or high value capacitor of the ceramic type. So those are some of the limitations of the ceramic type of capacitors. The electrolytic type capacitor, which is constructed differently, usually, whereas the ceramic capacitor does not have a polarity positive or minus or positive or negative, the electrolytic capacitor does in fact have polarization, or it is polarized. There's a positive terminal and there's also a negative terminal, or positive and negative leads. And it's important when we insert it into a circuit and we apply supply voltage to it that we do not reverse polarity or go beyond the reverse polarity that it can handle, because it can damage the capacitor, it can short circuit the capacitor, it may in fact fry the what you call the dielectric layer. And if that happens, it can actually overheat, swell, and maybe even explode, right? So that's, again, safety first. We need to be aware of that with electrolytics. Whereas the ceramic capacitor, you can swap it around. Doesn't matter, it doesn't have any polarity. Electrolytic capacitors do. And if you open up any circuit, a computer, a radio, anything that has discrete components like this, you're sure to see some of these pretty small ones, pretty large ones. Yeah. All right. What we also need to be aware of, whereas we said the ceramic type of capacitor is usually low values of capacitance, the electrolytic capacitor has a higher capacity or higher value, or can have potentially higher, much significantly higher values in as a capacitor. So let's come to some exam questions in relation to these points that we just made. Right, so these are the exam questions you're going to get. So the ceramic capacitor, a characteristic of low voltage ceramic capacitors is comparatively low cost. So they're pretty cheap, right? That's what you need to know for the exam. And in respect of the electrolytic capacitor, a characteristic of an electrolytic capacitor is high capacitance for a given volume, or in other words, for a given size. So you have this relatively small, but you have high capacitance in a very small package. And these are the exam questions. All right, let's come back and remind ourselves of what an inductor is, right? So an inductor is essentially a coil of wire, and this is a symbol for inductors, right? So remember, we dealt with it when we talked about transformers. We also talked a bit about it when we were talking about wire wound resistors, inductance as inductance, because it's a coil of wire. And you have different types of inductors or construction types, and we have them on your screen, all different types. And we'll be coming to one type called the toroidal core inductor shortly. All right. So the toroidal core inductor is, well, let's look on the right-hand side here. These are examples of what they will look like, right? Toroid, this is the shape that we have here, and that's why we call them toroidal core. And the material that is often used is called ferrite. So that's why we will call them a toroidal ferrite core inductor. Sometimes in short, we say a toroid, right? So it's toroidal, that's the shape, the three-dimensional shape. It's a toroid, so it's toroidal. Ferrite core, that means that this core that the coil is wrapped around is consisting of a material called ferrite. And we'll have a slide coming up shortly as to what ferrite might look like and the properties of ferrite. But the material of this core is ferrite. It's not a metal, or it's not wood, or it's not plastic. It's ferrite. That's the material. And it's an inductor. Why? Why is it an inductor? Because it's a coil of wire, and therefore it will have inductance. So that's just how we come up with the term toroidal, which is the 3D shape. Ferrite, because that's the material it's made of. It's a ferrite core. Inductor, because it has a coil of wire. And in short, we call it a toroid. And again, a toroidal ferrite core inductor, it consists of a coil of wire wound around a toroidal ferrite core. And we have an exam question that's associated with these toroidal ferrite core inductors. They have some advantages that we need to know for the exam. And they'll ask you in the exam, which of these are correct? And all of them are going to be correct. All of the points on that exam question, A, B, C, are all going to be correct. So we'll say all are correct. And what are those correct points? Well, the first one is, and we're talking about the advantages of these toroidal ferrite core inductors. One advantage is that you tend to have large values of inductance that you can get because you have wrapped the coil around the ferrite material. That significantly increases the inductance. If it were an air core, meaning that you just wrap the coil around air, there's no former, there's nothing inside of there, you will have inductance. But you put that toroidal material, that ferrite material inside of there, or wrap the coil around ferrite, and you significantly increase the inductance of that coil just by using that ferrite material inside of there. So that's an advantage of a toroidal ferrite core inductor. Large values of inductance may be obtained as compared to just a plain air core inductor. What's an air core inductor? Well, it's an inductor like this, just with a coil of wire, no filler material inside, certainly not ferrite. There's a second property or a second advantage of toroidal ferrite core inductors, and that is the magnetic properties of the core may be optimized for a specific range of frequencies. What that means is that the ferrite material could be constructed depending on the frequency that you're going to use this toroid in. So just bear that in mind. You can have different compositions, and we'll come to that in a little bit to see that we have what we call a mix, a different mix, right? So we can adjust the magnetic properties of this core by changing the mix. Again, we'll come to that in a little bit, but that's one of the advantages of a toroidal ferrite core inductor. The magnetic properties of the core may be optimized for a specific range of frequencies, and it will be less optimal for another frequency range, but you can choose the mix or the material for the frequency you intend to use if you're designing radio frequency circuits as an amateur radio operator. All right, so another advantage of toroids is most of the magnetic field is contained in the core. Now, what does that mean? Let's break that down. Most of the magnetic field is contained in the core. So if you just had an air core toroid, a lot of the magnetic lines of flux will be all over the place, all outside. But because you use this toroidal ferrite material as the core, most of the magnetic material will be contained or remain inside of here. And the advantage of that is in radio frequency circuits, you do not want this coil, the magnetic field associated with it, to go and influence another circuit component. Maybe you have another coil that's kind of nearby, that's maybe not well shielded, and you don't want to have that other core, that other coil affected. through the property of what we said, mutual inductance. Remember what mutual inductance was? We said if you have a coil of wire, you have an alternating current that's flowing in, and it's going back and forth. That magnetic lines of flux that goes outside will cut other conductors and introduce a current in them, right? So that's mutual inductance. So because you're using a toroidal ferrite core, it keeps most of the magnetic field within the core and less of it escapes or less of it goes outside to interfere with or impinge on another device or another component. All right. Again, exam question, and all of these are correct. All right, folks, we have a couple more slides and we'll be going just a little bit over this evening just to cover the material. All right, but we're almost there. All right, so we did promise to talk about ferrite material. And we need to know that there are different types of ferrite material. There can also be a different composition of the mix of material in making ferrite cores. So for example, the same way you're making dough, let's say if you are kneading bread, you'll use a particular mixture of bread and maybe baking powder or maybe yeast or something like that. If you're making roti, for those of us in Trinidad and Tobago, you might use a different mixture. The amount of water. If you baking a cake, you have different ratios of the components. So too, the ferrite material, you'll have different ratios of the mix, what we call the mix. So think of it as mixing flour, right? So you have a different mix of the ferrite material. Here's the toroidal core ferrite material raw. This is what it can look like as well. Different sizes, slightly different shapes and so on, but different mixes. And of course, how the material is mixed or made will affect how it performs in your radio frequency circuit. So that is very much calculated by the manufacturers of the ferrite cores. So the exam question associated with this bit of theory is the last bullet point. The composition or mix of the materials used determines the performance of a ferrite core at different frequencies. So what this is also saying is that if you want to use a ferrite core for a particular frequency range, you need to use a particular mix. That is what they're trying to tell you here. And if you use the wrong mix, well, you might not get the best performance or the particular type of performance that you want for the radio frequency that you're using that particular point in time. So if you're using VHF versus HF, or you may want a different mix. So that's what it means. So again, as a discerning amateur radio operator, you're aware of this. So you don't just go Amazon or wherever and you just buy any old ferrite core. You will now be saying, hey, what mix do I want? So this is where the knowledge comes in. As an amateur radio operator, you are aware of the theory, and therefore you can be very discerning and be very selective and correctly choosing your components when you want to make, let's say, something to reduce stray RF in your shack, for example, or you want to reduce interference. You know that the particular mix affects the performance on the particular frequency that you're using. All right. So a couple more slides. So a ferrite bead or core reduces common mode RF currents on the shield of coaxial cable by creating an impedance in the current path. So let's break this down. So this is an exam question, and we did a little diagram to show what we mean by this point, right? So we have our radio, our transceiver, and then we have our antenna. So remember, as amateur radio operators, what we're trying to do here, we're trying to talk into this radio or use a computer to connect to the radio to do a digital mode. And we want that radio frequency to go through down the transmission line or down the coax to the antenna. And we want our antenna to radiate that signal into space, the bunks of the ionosphere, and to speak to someone a couple of thousand kilometers across the globe. That's what we're trying to do as amateur radio operators. But sometimes you can have a current that's created, or what you call common mode RF current, that could cause, you have current in your shack. You don't want that. You want to be protected against that sort of thing. So what you can create is sometimes what you call a balun, they call it, or a matching transformer, sometimes people call it, but it's really taking the coax and wrapping it a few times around the toroidal core. And this toroidal core here will reduce the common mode current that can exist along this transmission line. But how does it do it? It creates an impedance in the current path. So just by putting your coaxial and wrapping it a few times around this ferrite core will reduce that common mode RF current on the line because it presents an impedance in the current path. And that's an exam question and you need to learn this. But we have just shown and illustrated. This is the coil around the toroidal core here. It's going to keep RF out of your shack, and this is what many hams do to be safe. And we just a little point that we make here, these ferrite cores, or the beads in some cases, provide the inductance. That's what it does. It introduces inductance to reduce or eliminate the RF currents that may cause RF feedback, which can cause equipment to malfunction. And it can also be a safety issue in your amateur radio shack where your radio and transmitting equipment is. So a good idea to use these ferrite beads to reduce that current mode RF current. All right, so last slide, the concept of self-resonance. So again, remember, an inductor is a coil of wire, right? But just because an inductor has inductance, that does not mean it only has inductance, right? It may have other things. It may have resistance, for example. It may have capacitance. It may have other properties. So components are not necessarily always perfect. So an inductor is not necessarily a perfect inductor. It may have other properties as well. And when it comes to radio frequency, depending on the radio frequency value that you're using, that can be different for different frequencies, right? So it is known that inductors can also have capacitance, that what we refer to as parasitic capacitance. And we need to bear that in mind as amateur radio operators. Now that parasitic capacitance, or what we'll say unwanted capacitance, right? That's why we call it parasitic. It's not really wanted, it's not really desirable, but it's there, but we need to be aware of it, right? It's not a perfect inductor. Inductors may not be perfect. And we need to be aware of that capacitance that exists. The reason we need to be aware of that parasitic capacitance is because it will cause that inductor to resonate at a particular frequency that is called the self-resonant frequency. So again, this is not necessarily part of the exam in terms of the formula, but we are showing what the formula for the self-resonant frequency is. It's 1 all over 2 pi the root of LC. What is LC? L is the value of the inductor, C is the value of the capacitance. So L for inductor, C for capacitance. Pi is the number 3.142 approximately, and 2 is just the number 2. So 2 multiplied by pi multiplied by square root of L multiplied by C, and the reciprocal of it, which is 1 over. So that is the formula. You don't need to learn it for the exam as such, but we're just giving you an idea. That self-resonant frequency, you can actually calculate it, right? Because you have that, it's an inductor, yes, but it has this parasitic capacitance. And we have a little graph here that shows where that SRF, or self-resonant frequency, exists. And there's a property about that SRF that we need to be aware of for the exam, right? But let us also recognize that the point of where this SRF occurs is that the impedance becomes so high that the circuit might actually appear to be an open circuit. So that's the reason why we need to know about this parasitic capacitance and where it occurs and where the SRF for that particular inductor is. So we need to be aware when we're using the inductor at a particular frequency, it may operate pretty well and serve as an inductor for some frequencies, but there's going to be a frequency at which it will not serve the purpose. It will actually appear as an open circuit at that AC value or that radio frequency value, and that's called the SRF. And we just have a little graph to show that the inductor operates pretty flat line here, 500 megahertz, 1000 megahertz, 1.5 gigahertz. But notice that about 2 gigahertz or so, all of a sudden the inductance is going up, and notice the impedance is going up as well. And that is due to the parasitic capacitance. And we have essentially an open circuit at that point, and the inductor will not perform at that particular frequency. So that's why we need to be aware when we use an inductor, the range of frequencies and within which it will operate as an inductor, and a frequency that, or the frequency range that will operate as essentially an open circuit, right? So this is AC, or this is radio frequency we're talking about. And that's the exam question. When an inductor is operated above its self-resonant frequency, its reactance increases. In other words, it becomes capacitive. And we need to know that for the exam. And we also need to, this corollary, or rather another way of looking at it, is that that inductor only acts as an inductor up to the SRF. So all here, it's operating as an inductor. And then at the SRF and above, well, you see it's problematic, right? So we need to know this for the exam. When an inductor is operated above its SRF, the reactance increases significantly, right? So again, little calculation if anybody's interested, extra information, what frequency the SRF occurs, you can actually work it out. Not necessary to know for the exam, but a little bit of extra information to understand. All right, so that's the last slide for the theory, and we'll come straight now to our question pool, where we will deal with all of the questions that covers the theory that we would have dealt with this evening. All right, so on your screen, we have, again, we're using the No Nonsense General Class License Study Guide. Anyone that's following who has the book, we are on between pages 15 to 20 for this evening. So that's where we're taking the question pool information from. So let's go. First question up. What causes a voltage to appear across the secondary winding of a transformer when an AC voltage source is connected across its primary winding? Let's dissect this question. What are they asking us? They say, what causes a voltage? So they're looking for a property or phenomenon that causes that voltage to appear across the secondary winding of a transformer. So what causes that voltage to appear across the secondary winding of the transformer? When what? When an alternating current voltage source is connected across its primary. So you apply an AC voltage to the primary, and we know what happens in a transformer because of that property that we're talking about. It causes induced voltage on the other side, which is the secondary. What causes that is the property or the phenomenon known as mutual inductance. Once you have AC, alternating current, on the primary side of the transformer, due to mutual inductance, it induces those magnetic lines of flux, will cut the coil on the secondary side and induce a voltage there as well, and cause a current flow to occur. And the property, that magnetic property, is called mutual inductance. All right. Next question in the question pool. Again, we covered all of this theory. What is the voltage output of a transformer with a 500 turn primary and a 1500 turn secondary when a 120 volt AC is applied to the primary? So let's dissect this question. Again, we did this as a worked example, but let's dissect the question again. What are they asking us? What is the voltage output? So we know the answer will be something volts, some amount of voltage, right? Something volts. That's the answer that we're looking for. And they're asking us in respect of a transformer. What does a transformer do? Well, it does two things that we learned this evening. It transforms impedances, but it can also transform voltages. And we did the formula for that. We showed that the ratio of the voltage is in relation to the ratio of the number of turns of the primary to the secondary. And using that trusty formula of the secondary voltage equal to the primary voltage multiplied by the turns ratio, and the turns ratio was the primary number of turns over the secondary number of turns. They gave us all of that information, the number of primary turns, secondary turns, and the input voltage. When we plug that into that trusty formula, we end up with 360 volts. We worked that out this evening, just a short while ago. Next question in the question pool. What is the output voltage if an input signal is applied to the secondary winding of a 4-to-1 voltage step-down transformer instead of the primary winding? Okay, so remember, this is a case where we have a step-down transformer, but we are applying the input to what is normally be the output, which is the secondary, right? So instead of applying the voltage to the primary, we are actually applying it to the secondary, and therefore the voltage will be induced on the primary side. But if it's a 4-to-1, which would normally reduce it to a quarter from the primary to the secondary, if we go the other way from the secondary to the primary, what it does is 4 times, and that is the answer. The voltage is multiplied by 4. All right, next question in the question pool. Why is the primary winding wire of a voltage step-up transformer usually a larger size than that of the secondary winding? So we had said that the reason for that is because the current is higher in the primary. That is why we have a larger wire to cater for the larger current in the primary, because it's a step-up transformer. Therefore, we go in for a lower voltage to higher voltage, and therefore the current will be less on the secondary. So what that means is the current will be higher on the primary, and that's it, to accommodate the higher current of the primary. Next question in the question pool. What transformer turns ratio matches an antenna's 600 ohm feed point impedance to a 50 ohm coaxial cable? So let's dissect this question. So we did a little diagram where we showed you the radio and the antenna, and of course we actually put a matching circuit there as well. So we're looking for a transformer turns ratio. So we need to work out the turns ratio. And remember, we gave the formula of the turns ratio is equal to the square root all of the output impedance over the input impedance. And they gave us that, the output impedance and the input impedance. So therefore, we work that out using our trusty formula, and we get 3.5 to 1 is the ratio. Okay. All right, so let's continue with some of the other questions for the theory. Why should wire wound resistors not be used in RF circuits? Well, it's simply because wire wound resistors are a coil, and a coil will have inductance. And at RF frequencies or alternating current, well, it introduces reactance. So therefore, the reason is that the resistor's inductance, again, it's a coil of wire, could make circuit performance unpredictable because we're introducing inductive reactance where we didn't want it, and therefore circuit may maloperate. All right. Next up, which of the following is characteristic of low voltage ceramic capacitors? Remember, we showed the difference between ceramic capacitors and electrolytic capacitors, advantages and disadvantages, pros and cons. So we did say one of the good properties of the ceramic type of capacitors is that it's relatively low in cost. So comparatively low cost is the answer. Next capacitor question, this time electrolytic. Which of the following is characteristic of an electrolytic capacitor? So we said that electrolytic capacitors, for its size, can have high capacitance value. So that's the answer. High capacitance for a given volume or size of capacitor. All right, packs a little punch in a small package. All right. Next question in the question pool. What is an advantage of using a ferrite core toroidal inductor? So what is an advantage? So we had given a series of advantages, and we said all of them are correct, and you'll get them in your question pool as all of these choices are correct. So that's the answer. All of these choices are correct. What are they? Large values of inductance may be obtained. The magnetic properties of the core may be optimized for a specific range of frequencies, and most of the magnetic field is contained in the core. We stated that all of these are advantages of a ferrite core toroidal inductors. So that's why all of these choices are correct. Now remember in the exam, this A, B, C, D may not be in the same order. So that's why learning whether A is or B or C is correct or D is correct for a particular question, it could be mixed up in the exam. So try not to do that. Try not to learn that D is the answer. All these choices are correct, maybe B in the actual exam question, right? So bear that in mind, please. All right. What determines the performance of a ferrite core at different frequencies? So we said the thing that determines that performance is the mix of the material that is used to construct the ferrite core. So the answer is the composition or mix of materials used. Next question in the question pool. How does a ferrite bead or core reduce common mode RF current on the shield of a coaxial cable? Let's dissect this question a little bit. So remember I said we use ferrite beads or ferrite cores to reduce that stray current, which could damage or could cause maloperation in your shack, or it may actually cause a safety concern as well. But how does it work, that ferrite core? Well, we take the coaxial cable and wrap it around it, and it creates an impedance in the current path. So that's how the ferrite core, the ferrite beads work. It creates an impedance in the current's path. All right. Next question in the question pool. What happens when an inductor is operated above its self-resonant frequency, or what we call the SRF? What happens? Well, it becomes capacitive, right? That's the answer. And I think that's the last question in the question pool for this evening. So let's just go back to our slide deck. All right, so folks, again, if you have any questions, please send an email to this email address or send a WhatsApp to this number, and we will treat with it as the start of the next session. Any questions? Also, as mentioned last week, we now have a WhatsApp channel that we'll be providing updates on. Some persons, it may be more convenient to you to get the updates there as well. We do send out emails at least once per week. So please check your email. Now you have an alternative way of getting that bit of information as well as other information that we normally distribute in respect of things like weather information and other important radio related news, right? So please feel free to join this channel. The link is on your screen. You'll get it in your slide deck when we publish it. It's in last week's slide deck as well. So you can either write it down, take a screenshot, or you can wait until you get the slide deck and you can simply click on it if you wish. So whichever works better for you, we encourage you to consider joining this channel so that you can be up to date. All right, so folks, our next session will be, God's willing, next Friday, the 24th of November at the same time, 8:30 p.m. All right, so thanks for the little bit of extra time, folks. We do appreciate you being in the class, your attention, highly appreciated, and we expect that you will be successful in the exams. Those of you who are taking this course, we do appreciate the time that is spent with us. So do have a good night. All the best. Have a great weekend. Be safe, everyone. Take good care and see you next week.